let's look at how we understand what the interior of a terrestrial planet, Earth, is like. Now, for perspective, how can we make claims of stuff about the Earth having a solid inner core, surrounded by liquid, outer, then mantle, and then a crust? The deepest that we've ever dealt a hole is maybe about 10 kilometers deep. And that only gets you through just the outer layers of the crust. The outer crust layer is almost 100 kilometers thick. So how is it that we can know about the interior regions of the planet? Well, that's through studying earthquakes, actually. There are two main types of waves that we'll talk about: primary and secondary waves. So let's split this up a little bit and talk about the primary waves first. The primary, or for shorthand we'll call them P waves, they can travel through basically anything. They can travel through solids or through liquids, and they're a type of longitudinal waves. So in this picture, at the top here was the epicenter where the earthquake started. And these quakes are basically waves, and as waves propagate through material, they will bend. Think back to light as it bends when it refracts passing through material. It's a similar property. It's the wave itself refracting as it passes through mediums. Now, if we have a planet that has this liquid region, you'll see this sharp bend, exactly like a light wave coming in and refracting. And look at the consequence. We have this mantle here, this P wave comes in, it'll hit a liquid region of the core, and you'll create this region where none of the P waves can be detected on the other side of the planet. We'd call this a shadow. So if there is a earthquake that happens here, and you have seismometers throughout the planet's surface, then you can say, hey, we detected P waves all the way here, but then your neighbors, shadow, then you start getting a P wave again. Well, what that tells you is that the size of the shadow, it's directly related to the size of the liquid region, where you have the P wave that initially came in, refracted, and exited out, refracting again. The size of this shadow tells you how big the liquid region of the core is. Switching to the secondary or S waves. These are transverse waves, and they can only travel through the solid parts material. And once again, here's the epicenter and your S waves. Well, they'll refract as they travel through material, traveling through the different densities of the mantle. But S waves cannot pass through a liquid region. It's only through solids that S waves can be transmitted through. And so what happens is that if there is a liquid core, then measuring from the epicenter, there will be this large shadow where there just will be no S waves detected. And this gives you another useful tool of comparing, hey, if there was an earthquake here, where do the S waves get cut off? And that also helps you measure how big this liquid core is. Here are some animations to help us visualize what we mean by S and P waves. Look at how the S waves come in. They are what we call longitudinal or compression waves. As the source compresses a region, it will propagate down material, squeezing and stretching as it propagates down. Some of our primary waves, these are good for through solids and liquids. Now for our S, our secondary waves, they are transverse. The direction that the wave is traveling versus the direction of the wave motion. So the wave is going up and down in an S wave, but it's traveling in this picture, the X direction. So let's apply the knowledge that we've been talking about. Let's say we've moved to another planet, and on that planet you're at the epicenter of an earthquake. Strange name, calling it an earthquake, but we'll call it an earthquake. And a scientist on the other side of the planet detects only P waves. What information does this tell us about the interior of that planet? What have we learned from this one experiment? Go ahead and pause the video, go back to the previous figure to help you come up with the answer, and come back. So your companion finding only P waves gives you enough information to say, hey, at least part of this planet's interior is liquid. If there was no liquid, if there was no bounding region here, then there would no be a shadow of a P wave. You can't definitively rule this out. Your companion is probably somewhere in this region on this planet here, where they're detecting only P waves, and they're in the shadow of the S waves. If they're there. We don't know. We don't have enough information. But it's possible that you're just in the shadow of the S waves due to the presence of this liquid outer core. You don't have enough information to eliminate the possibility of the solid inner core. You need more information or more earthquakes to happen. Looking at Earth in a bit more detail specifically, we can divide ourselves up into the crust, the mantle, and then the core. So let's go through this here. Our crust is the material we live on, right? The low-density granites and solids and all the ocean waters on the surface layers. And the crust is about 100 kilometers deep. Obviously, there are variances across the entirety of the planet. But on average, you're looking at a crust that's at a depth of about 100 kilometers. And we've only peered about 10 kilometers deep. We haven't gone very deep into this planet's surface. Underneath the crust, you'll find the mantle, which is where the bulk of Earth's volume is going to be. It's the largest section. It goes to about 3,000 kilometers underneath the surface of the planet. Outside that, you're going to have a region of this liquid core and a solid core, a dense, hot core at the center. And all that goes down to about 6,300 kilometers, the radius of the planet. So we know our core is going to be composed of these dense materials like iron and nickel, which will come up relevant for us, remember, because Earth has a strong magnetic field, and iron and nickel, well, those are two of the ferromagnetic materials. As for the distribution, where materials are being found, well, that is produced by differentiation. Think of it this way. The dense materials will sink down to the core. The denser you are, the deeper into the well you'll go. Whereas the light materials kind of floated up top. Think of pictures of oil floating on top of water. Things like that. Now, the deeper into the planet you go, the hotter it's going to be and the more pressure is there. The temperature, well, that comes from the formation energy. Think back to the planetesimals forming from the nebula collapsing. That's what I mean by formation energy. And the remaining temperature, the remaining heat, well, that's radioactive material in the core decaying. Part of how we discovered radioactivity was understanding how hot the interior of the planet is. Now, the smaller planets, or the moons, they're going to lose their heat faster than the larger ones. And the best analogy I can give you is, say you baking two potatoes, right? You get them to the same temperature, well, which one's going to cool off faster? The smaller potato is going to cool faster. And it's because of this ratio between the surface area and volume. That small potato proportionally has a greater surface area per volume to radiate its thermal energy away. And the same applies for size of the planets, right? The smaller planets will be able to cool off faster. Now, at least on Earth and Mercury, we have this substantial magnetic field. A shorthand model is to think of it as having a bar magnet on the center of Earth, where we have a north magnetic pole and a south magnetic pole, creating these field lines pointing in this direction, right? We understand some of what's generating this magnetic field that's protecting this planet and our atmosphere from all sorts of cosmic stray radiation, but we don't have the full picture. We know it's something to do with that iron nickel coal rotating rapidly. The rotation of these materials is what's creating these fields. We also know over time, by studying the iron minerals throughout the planet, we know that the orientation of these poles versus south magnetic pole or north magnetic pole, we know that flips over time. Now, comparing to some of the other objects, like, say, Venus, from what we can tell, we know Venus should have an iron-rich molten core, but it doesn't have any sort of significant magnetic field. And our best speculation goes back to Venus's sidereal rotation. It's long day. One day on Venus is about 243 Earth days. We suspect that reduced rotation rate causes Venus to have a much weaker magnetic field.